motivation of this study is recent increasing and some food price spikes happen in the latter half of the 2000 with some food price spikes. So some people believe that some climatic extremes like a drought play a role to some degree to lead to such kind of the food price spikes and some food insecurity for poors. So so the monitoring and prediction of climate-induced variations in crop yield, production, and export amounts have become increasingly important for national governments and commercial entities in food importing countries like Japan. And especially prediction of yield is more important than that of the harvested area because of its large year-to-year variability. However, to do so, global gridded historical yield information is completely lacking when I studied this global analysis about 4 years ago. So I had to study it to develop the global dataset of historical yield. So I combined FAO country yield statistics with satellite-derived net primary productions. And we used the information on the harvested area and crop calendar around the 2000, and some information about the cropping systems come from the USDA. So we combined this information into one single data set and validated substantially by comparing with independently collected subnational yield statistics in the 23 major producing countries. So the yield data value I used in this study is rather modeled yield, not actual or not observed or reported one. So honestly, for the major growing areas, my yield estimate is quite reliable, but not so reliable for the minor growing areas because of the mixer problem on the satellite product. So by examining this data set, we found that some historical change in yield in recent decades. So I calculated the coefficient of variations for different two periods, in this case for wheat yield, then calculated the difference between them like that. So recently the red color indicates increased instability of wheat yield, mainly in the southern hemisphere, including Australia, which is one of major wheat exporter. So this result reinforced the importance of monitoring and predicting the yield variability at the global scale, especially for the food importing countries. So the first question to this data is to what extent of the world harvested area can climate explain year-to-year variation in yield? I'm not sure this question this is grammatically correct, but anyway. So many speakers mentioned that what growth stage is more important for deriving climate yield relationship. So in this case for rice, this line indicates above ground biomass and leaf numbers, and it's a formation of the grain. So as many presenters suggest that the reproductive growth period, its climate condition is more relevant to explain the yield. Of course, climate condition in vegetation growth is also important, but in this study we selected this period. And one thing that is important to be accounted for is what climatic factor is the most constraint of crop yield. So this work done by the Nemani and published in the Science shows that the vegetation activity across the world is determined by different climatic constraints like radiation, water, and temperature. Unfortunately, this map is for the natural vegetation but not agricultural ecosystem, but have some implications for agriculture. So, and more practically, which months do correspond to the reproductive growth period for a given crop area combinations? This is a key information. So I used the global crop calendars and specified the 3-month period before the harvest as a reproductive growth period for a given cropping season and crop. I agree that the 3-month period is too long to call the to be an exact reproductive growth period, but this 3-month period is selected to cover the entire reproductive growth period, considering the relatively poor accuracy of the crop calendar at the global scale. And the dependent variable in this study is the yield anomalies or yield differences relative to the previous year, normalized by the 3-year running mean. And dependent variables is temperature and soil moisture. That is its first differences and 3 months average during the reproductive growth stage. And regression coefficient were estimated for each crop and cropping system. In this case, it means growing seasons and grid cells. So the data come from the for yield. We use a global data set of physical yield I already talked about. And for meteorological parameters, we used reanalysis data developed by the Japan Meteorological Agency called JRA25, because this reanalysis including soil moisture. And we use a global crop calendar from the SAGE. SAGE stands for the Center for the Sustainability and Global Environment at the University of Wisconsin-Madison. So this data set looks like that. So the original grid size of this data set is 5 minutes arc, but as you can see, the exact data quality is for the country level. So by using the ribbon out cross-validation techniques, we've quantified that the climate information, in this case temperature and soil moisture, could explain the yield variability in the roughly 30 to 40% of the global harvested area, colored in orange. In this case, the measure is a coefficient of determination between the predicted and the reference yield anomalies during the 25 years. And coefficient of variations, it is significant at 5% level, means this prediction method can, the climate information, yield variability can be explained reliably by climate information alone. So next question is how can one reliably predict year-to-year variations in yield at lead times that allow such information to be of value to government and commercial concerns? So the JAMSTEC stands for the Japan Agency for Marine and Earth Science. and technology. This provides operational seasonal forecasts at a global scale. So the Jamstack provided 1 year-long seasonal forecast every month. So I use this monthly forecast to calculate the 3 months mean average for temperature and soil moisture. So the real time corresponds to the 3 months for the within season predictions. I also examined the pre-season predictions that have a 5 months lead time, but today I just talk about this result. So using a seasonal forecast provided by Jamstacks, our result is that crop prediction at 3 months before the harvest could be reliable, means a significant coefficient of variation, coefficient of determinations in roughly 20% of the global harvested area, colored in orange too. So, however, we found the difference in the crop forecast skill across the crop types. So rice and wheat are reliable when we examining the global mean, at the global scale. I compare the seasonal cropping forecast with random predictions. This means that I pulled referenced yield anomaly data, then randomly sampling from the pooled data. So if we compared these different predictions, so using seasonal forecast for rice and wheat, the global harvested area where the crop prediction is reliable is far larger and significantly larger compared with random prediction for wheat and rice. But unluckily, maize and soybean, the 3 months lead prediction is relatively better than the random prediction, but this is not significant. So I can say the 3 months lead predictions for maize and soybean is better than the random forecast from this result. However, this doesn't mean that maize and soybean prediction is useless, because for some countries like Indonesia and India, both 3 months lead, this is a within season prediction and the pre-season prediction, both work with with better correlations like that. So what caused the difference in crop prediction skill according across different crops? That is the next questions. So I derived the sensitivity of yield anomalies to the unit change in the temperature or soil moisture by solving these equations. Because we use multiple regression models, we can derive such linear responses to respective independent variables. So at the global scale, maize and soybean is more soil water sensitive, indicated by blue. And more than 50% of the global harvested area is sensitive to the soil moisture. However, rice and wheat, the majority of the global harvested area is more sensitive to temperature compared with soil moisture. And you may know that the temperature forecast is always more reliable than any other moisture forecast, including soil moisture. And in general, the climate forecast in the low latitude in tropical area is more reliable compared with predictions in the middle and higher latitude. So this results in the differences. The rice and wheat is more dependent on temperature forecast scale, dependent on temperature, and temperature forecast scale is more higher than the soil moisture. Then, and the global prediction on rice and wheat have a higher scale compared with the soybean and maize predictions. Of course, some other factors like agronomic technologies affect this result. The good example is rice. The rice is extensively irrigated. So in this case, soil moisture doesn't have a rule to explain the yield variations. In this case, temperature is more important rule to explain the yield variability. And again, the temperature forecasts have a higher scale. So after getting this result, that in the about 20% of the global harvested area, the reliable crop prediction is available for that area. This is scientifically interesting, but insufficient for the operational or insufficient for users like food agencies and food security analysis. So I asked how and to what extent can one improve the scale of global crop predictions over and beyond the 20% of the global harvested area. So I introduced the concept of the categories of crop prediction scale. This can be represented by two axes. X-axis represented the climate forecast scale from low to high, and y-axis represented the degree of climate crop relationship from weak to strong. So the skillful crop prediction is really expected if the given crop area combination fall within the category 1, because this area has a high climate forecast scale and strong climate crop relationships. However, for the category 4, so even though the climate forecast scale is high, the climate crop relationship is weak. This could be happen when the political or socioeconomic factors drives yield changes. And for the category 2, although the climate crop relationships is very high, is sufficiently high, but climate prediction scale is low. So in this case, improvement of the climate forecast scale would increasing the crop prediction scale. So I used multiple regression models. So we can, the coefficient of determinations between observed and simulated yield anomaly. This can be used as a measure for the y-axis, and coefficient of determinations between the predicted and observed temperature or soil moisture can be used as a measure for the y-axis. So I mapped this category on the global map. So you can see that the green, this means category 2, occupied a higher percentage of the global harvested area. So clearly, the wheat in the Australia have fall within the category 1, indicate a high predictability of crop yield. So I aggregated this grid cell map to the latitudinal bin. Then we found that yes, there is some big, not a hotspot, it's a big mass. indicating North America and Brazil and Argentina. This have a large potential to increasing cropping prediction by improving the climate forecast. And yes, and I re-aggregated it for the seasons from. So this corresponds to the North America. This is reproductive growth period from July, August, September to October. And for the Brazil and Argentina, it corresponds to the February, March, April. So this is a take-home message for the climate scientists to improve the crop predictions. The target area to improve the climate forecast, especially for the agriculture application, it's the seasons and these seasons and these latitudinal bins. However, it is in general very hard to improve the climate forecast scale for specific regions and specific seasons. It takes a long time to improve the forecast skill in climate. So my next question is that is there any reliable information that is derivable from seasonal climate forecast and linkable to crop yield? Because temperature and soil moisture forecast is not sufficient due to its poor skill in some regions. So I focused on the ENSO index, El Niño Southern Oscillation Index, because one of my, you may know, and ENSO in the, how to say it? And my colleagues at the Australian Bureau of Meteorology, Ginger Luo, reported this result. ENSO forecast skillful even at 1 year lead times. So among the other variables, climate variables, the ENSO index is the most the highest skill compared with temperature and other bioclimatic variables. So I try to link ENSO phase with yield variability. So for instance, the 1983, that is this is Niño 3.4 SST anomalies, or the oceanic Niño index. In this year, the ENSO phase matured to be the El Niño, then rapidly decreased to the cooler phase La Niña. And if we consider about the cropping calendar in southern hemisphere, correspond to the August, September, October to November, this corresponds to the La Niña phase. However, in contrast, in the mid-latitudes of the northern hemisphere, this reproductive growth period corresponds to the May, June, July to August. So the ENSO phase still in the warmer phase. So this indicates the reproductive growth growth period in this area corresponds to the El Niño, and some area correspond to the neutral because of this. So by using this concept, I assigned each year for El Niño or La Niña and neutral. In this case, that is an example for the wheat yield in Goody Windy, Australia, because Roger Stones published in Nature the very strong relationship between ENSO and wheat yield in this area. So I think this is a good test case. So by using a 5-year running mean as a normal yield, we derived the yield anomalies, that is a percentage to the normal yield. And blue indicates La Nina years, and orange indicates El Nino years. Then we take an average like that. So clearly, in ENSO El Nino years, the wheat yield here, this area decreased compared with the neutral years. And in the La Nina years, the wheat yield is above normal, but a little bit smaller than compared with the neutral years. This indicates negative impact of both El Nino and La Nina compared with the neutral years. Of course, there is issues about the statistical significance between them, but just compare with the mean values, there is a negative impact. So I applied this analysis to the grid cell yield and mapped the impact of the, in this case, El Nino relative to the neutral years. So for maize, the significant negative impact colored in red appeared many parts of the world, including the high latitude. And however, some positive impact appears in the South America, and quite different response for the soybean. Both North America and South America shows positive response to the El Ninos. And this is a La Nina case. Clearly, La Nina shows less extent of the significant positive and negative impact compared with those of the El Nino years. But important thing is that there is a significant relationship between the ENSO phase and long-term mean yield anomalies, even in the high and mid latitude. This suggests that the possibility to predict the yield anomaly in these areas using ENSO index. But this hypothesis should be tested. Anyway, we combined these grid cell yield anomalies to be the global mean yield anomalies weighted by the grid cell harvested area. So maize showed that the maize yield anomaly is significant and negatively affected in the El Nino years in red compared with La Nina and neutral years. However, soybean yield anomaly behaved differently. The positive impact of the El Nino or soybean. And for rice and wheat, more negative impact is happened when La Nina take place, even compared with El Nino years.
Most of those areas are in South America?
South America, both North America and South America get a positive impact.
Why maize? Because they usually plant in South America, for example.
Yeah.
They plant around September, October.
Mm-hmm.
Maize, they plant around September, October.
Mm-hmm.
And soybean, probably November. During El Nino, the effect of El Nino is somewhat wet.
Mm-hmm.
That's why probably the soybean, when it's El Nino, it's positive.
Oh.
Why maize?
Okay.
This is negative.
Uh-huh. Yeah, I also map this, but I'm not exactly sure which regions were responsible.
Maybe maize is not only dominated by South and North America, maybe other areas as well.
Mm-hmm. Mm-hmm. Okay. And I have to say that we need caution to read these figures because in real world, the El Nino or La Nina happens But this figure is calculated the long-term mean impact when the reproductive growth period for each grid cell is corresponded to the El Niño or La Niña or neutral. So anyway, let me summarize until here. The recent food price spike and change in the year-to-year variation in yield of major crops increase, and the need for the global crop prediction and monitoring. And climate is a key driver of yield variability, and variations in yield about 20% of the global harvested area can be predicted 3 months before the harvest. And the limiting factor of the reliable crop prediction vary by crop and region, but the improvement of scenario climatic forecast is a key to read a better crop prediction compared with increasing the climate crop relationships. And effort to improve global crop predictions like ENSO index-based methods ongoing, and global agricultural geography is one of the important correlators for global crop predictions. So I would like to introduce some ongoing works. The one is this question: in which regions and crops is the ENSO-based crop prediction method is more reliable than the seasonal temperature and soil moisture forecast-based crop predictions? So as you know, the ENSO index has a more higher prediction skill. So compare with seasonal temperature and soil moisture predictions. However, in the statistical crop model, the independent variable is 2, but it decreased to the 1. So it is potentially using an ENSO index potentially decrease the climate crop relationships. So I'm not sure using this method finally increasing the finally reach here or stay around here. So this should be tested. And however, this ENSO index-based prediction method is now applied to inform the Ministry of Agriculture, Forestry, Fisheries, Japan about possible variations in yield across the major producing countries for the preparation of the possible 20,000 summer for El Niño events. I'm not sure if the El Niño is already onset or disappear, but this prediction is provided and released in the last July. And as far as I know, this is first crop official crop predictions released in Japan with real time of the 1 month to the 6 months, depending on the grid cell. And anyway. And second ongoing work is that how can crop prediction using process-based crop model be more value added for users than statistical crop models? So my team is developing a global crop model called PRESB2. This is based on the growing degradase phenology and Parker photosynthesis model, and inclusion of the downregulation of the photosynthesis rate, and to leaf canopy and soil water assessment tool-based root development and soil water balance. And this model is operated at the grid size of about 1 degree using reanalysis data as a forcing data. So, and but this model don't have a capability to simulate the yield trend. So the subscribed linear yield trend is used now. So this is an example for the maize and soybean for 3 major countries, United States, Brazil, and China. And circle indicates observations, and lines and shade indicates model simulations. So this is the result based on the cross validations. So this model have a quite good performance in simulating the crop yield using observed weather data. However, the spatial pattern in the year 2001 is like that. So we know that some issues on the interpolation of the crop parameters for some areas where the reference data are not available. But anyway, the general geographical pattern is quite nice compared with the reference data. However, we are afraid this. The process-based model in general have a very high capability to explain the climate yield relationships using daily weather data. But the climate forecast scale at daily time scale derived from the season forecast may be low compared with the 3 months average. So the method combined with the process-based model and daily forecast data would locate here. So I'm not sure this approach can overcome the statistical crop model. So I need to test. And this is the last slide. And improve our understanding on where, when, how, and what crop is grown across the world. This is a key information to predict the crop yield and growth. And at this moment of time, only the historical information is available only for the yield. And crop calendar and irrigation distribution and fertilizer input, such a management information is completely lacking. So we are interested in crop prediction and risk assessment, but this heavily dependent on the data sets and model. We can use the data assimilations, some speakers already introduced, but data assimilation itself is heavily dependent on the data set. Without data, we can't predict reliably. So that's the reason why our team is now put heavy much effort to develop historical crop informations like crop calendars by combining the satellite information and other different data sources.